Welcome to another episode of Epic Earth, a podcast for those curious about the STEM fields and the awesome, quirky, and fun experiences and research that is taking place right now. This is episode number 8, Rare Earth Rockstar of the East Coast. Sit back, relax, and enjoy the ride as we take a journey around this epic Earth.
Welcome, everyone, to another episode of Epic Earth. With me, I have my trusty sidekick, Brian Rosenblatt.
Hey, guys.
And today we have special guest, Graham Lederer. Hi, Graham.
Hi.
So Graham is a research geologist at the US Geological Survey in Reston, Virginia. And he's going to be telling us a little bit about what he does with that. He has a pretty extensive and cool academic background. He went to College of William and Mary for his bachelor's. He did a PhD at the University of California, Santa Barbara. I'm assuming you were there with Dan Luna when he was there.
That's right. Yeah, Dan and I were roommates.
Oh, nice. And you also did a postdoc at the Massachusetts Institute of Technology. Is that right?
Yep. Yeah, I was at MIT for about a year.
Awesome. Did you get to see Noam Chomsky in person?
No, but it was a pretty amazing place to be. I mean, just the special guests would come and give lectures. I had the privilege of working in Sam Bowring's lab at MIT, so one of the foremost uranium-lead geochronologists, and it was a really cool project. So
that's awesome.
We can talk more about that.
Okay, yeah, sure. I was out at a conference in Boston. This was a while back, and I got to see Noam Chomsky give a lecture out there during that conference. So he's one of my heroes. I love him. So it's cool that you got to go to MIT. What a cool place. Great. Well, Graham, do you want to tell us a little bit about what you do right now and how you sort of got into the geosciences?
Yeah. So, my background is really hard rock geology. So I've been fascinated by minerals and rocks since I was a pretty little kid. But now mostly what I do at the USGS is study mineral resources and especially critical minerals. So critical minerals are anything that's subject to a supply interruption. So it's maybe something that we import from other countries, or it's something that is limited in supply and we expect demand to increase, or maybe it's something that's only produced in one facility or one area in the world. So its supply is just inherently more risky. So a lot of my work. Oh, go ahead. Yeah.
Do you have an example of one of those minerals?
Yeah, I can give you 35 examples, but one of those, and that's in the news a lot today, is lithium. So lithium that's used in batteries, which is necessary for the green energy and electrification of vehicles. Another one that I've been working a lot on is tungsten, and tungsten is really interesting because you basically need tungsten to make the parts that you need to make anything else. So it's extremely hard and durable. We don't just use it in light bulbs anymore. In fact, we mostly don't use it in light bulbs. We use other materials. But for any type of cutting part or drilling or abrasive, tungsten carbide is kind of the go-to material. So yeah, pretty much you name it, there are critical minerals in some amount in almost every product we use or product used to make a product that we use.
That's great. That's what an interesting topic. How did you get into that specific research or field?
Yeah, it's a good question because when I started out in geology, I was not really thinking about the economic implications of studying rocks and minerals. I was just interested in the science and how magma systems worked, and field identification of rocks and mapping. So as part of my PhD, I was studying granites in the Himalaya, which sounds like it has no societal implication at all. But one of the reasons for that was trying to understand plate tectonics and crustal melting. And one of the best ways to do that is using uranium-led geochronology. So there are minerals like zircon that a lot of people might be familiar with. Well, maybe if they're into geology. There's another mineral called monazite, which is a rare earth phosphate mineral. It incorporates a little bit of uranium and thorium, and it makes it a really useful geochronometer, basically like a radiometric clock that starts ticking when a granite or magma crystallizes to form a rock. So I was approaching this question of how do crustal processes, melting, partial melting, crystallization work in the Himalaya, and using this rare earth mineral. And at the time, in 2010, there was what was called the rare earth crisis. So basically 100% of the world's rare earth production was concentrated in China. China and Japan had a trade dispute over some rights to fishing grounds offshore. And China implemented a restriction on exports of rare earths. And Japan, which is dependent on imports of rare earths to make things like permanent magnets or other products, was really concerned. So overnight, the price of rare earths, and that is all the lanthanide elements, so lanthanum, cerium, neodymium is a big one for magnets, dysprosium is another one, all the way through lutetium. So it's 14 different elements. The prices for some of those jumped up like 1,000%. So
Wow.
all of a sudden there was a impetus by the US government and governments across the world to really look at these supply chains and understand where these critical raw materials were being sourced. So that happened in 2010. I actually did an internship at the USGS in 2011 with the rare earth specialist. And that was kind of my foot in the door. And I've really enjoyed my work there ever since. So I finished up my PhD, did a postdoc, and then came back to the USGS now as a full-time researcher.
Wow, that's really interesting. And what a crazy way to fall into to that type of research. And I think it's funny because like you talk about like this rare earth crises that happened, and I don't know, that's 11 years now ago, and I don't even remember that. And to think like most people probably, or a lot of people don't probably understand where a lot of their products come from, right? They just go and buy them off the shelf and don't think about some of these crises that come up, or these production sort of mishaps that could go wrong. I think with the pandemic recently, this has come to more light because we're seeing some of those issues come to light again, such as manufacturing chips for phones and computers and such, and just how our world is basically based off of the economics of some of these elements that you're talking about.
Yeah, I was going to ask if the most recent strain to the supply chain has affected your work at all.
Definitely. Most directly in just trade. You hear reports of container ships, either not being able to dock or not having enough containers or things like that. That's probably the most direct impact. But there's also longer term supply disruptions that we're not even really thinking about yet. Things like, when production is shut down because of a pandemic, the time it takes for rock to be converted into a metal, and then that metal to be, put into products can be months, a year. I mean, some of the supply shortages that are happening now are 2 years in the making. So it's one of the most satisfying and I think rewarding parts of my job is I see things in the news, I see headlines, and I can think of how that relates to my work on like a daily basis. But it's also kind of strange, coming from geology where we think about things in very long time scales. We're used to throwing around millions or billions of years, no problem. And now we're talking about human time scales, which are much more rapid. There's an impact to actions and policies in a real time basis. So that's one thing that's definitely different from what I studied and went to school from or for. But the other thing about the pandemic is it's kind of brought into people's awareness and this conversation about uncertainty. And it's something that as scientists, we need to do a better job of communicating uncertainty. And I've seen great visuals come out of different media outlets, and people are now more familiar with things like confidence intervals and the uncertainties of predictions and stuff like that. So that's something that is a big part of my current work, which is trying to predict where future resources are going to come from on Earth. So, those two skills, I'll say, dealing with different timescales and dealing with uncertainty, they're not unique to the geosciences, but I think it's something that Earth scientists are very aware of and familiar with, and are just vital for almost any application, whether or not they end up doing that as part of their job later on.
Absolutely. I think that's a really important point that you highlight there. Yeah, there is a lot of uncertainty. I think the way that we communicate that absolutely is important to the communities. I know working with volcanoes, there's a lot of uncertainty in things like eruptions and how far something will travel, like a lava flow or a lahar, or and yeah, it's relaying the information and being able to say, hey, we're getting better at predicting these things, or we're getting better at measuring them, but it's not a perfect science. And there are things within it that we don't know about, but that we're certainly trying to discover. And it's not like we're hiding information from people. It's just that we have to be able to at better communicating what we don't know in the science as well. Not just
Exactly.
Yeah,
And
great point.
that's another awesome thing about working for the USGS is that it's a science organization. We don't set policy, we don't enforce policy, but we do the science that's needed for other people to make decisions. Mm-hmm. And that's, it's a privilege as a scientist to be able to work for an organization like that. It's also, a duty of ours to make sure we communicate that science to non-scientists in a way that allows them to make decisions. So I think you said it well. We're always getting better, but the best policy is to be honest with what we don't know, because that's just as important as what we do know.
Mm-hmm. Definitely. That's great. So what is the most fun thing that you do about your job, would you say?
Yeah. I got into geology mainly because I liked being outside and doing field work, and going way back to undergrad at William and Mary. My first interaction with the USGS was through an EdMap project. So that's where a handful of undergrad students, myself included, we got to map a 7.5-minute quadrangle in the Blue Ridge of Virginia. Oh, cool. So spend a summer, breaking rocks with a hammer and trying to sort through the saprolite, which coats all the blankets, basically all the bedrock in Virginia. And it was fantastic. I loved it. It was an awesome field experience, and I was totally hooked after that. So whenever I feel like I don't know, uninspired or need a little boost, I I try to get out in the field and actually look at rocks, because, there's only so much you can appreciate and understand behind the computer screen. And, going back to being honest about what you don't know, I've never been to an outcrop where I understand everything that's going on, right? So it's humbling to get out in nature and realize, oh yeah, there's a lot more going on.
Yeah, that's very true. I think for all people in geoscience, we come into our field knowing a little bit, and there's a whole lot that we don't know. And then when it's applied, right, when you go out and you like see these things out in the real world, you're like, oh yeah, like I really don't understand like a lot of this stuff that's going on, like, right? Because behind the computer, a lot of it's theoretical, or it's like numerical modeling, or it's modeling of some sort, and or quantifying, in numbers. And then we get out in the real world, and there are other things which are acting on those processes that maybe we don't understand, or that we're just starting to like really piece together basically with what's actually happening, which is super cool. So like, in my opinion, I think that it's awesome that there's so many things that that we have left to discover, and just on our own planet. And so is there like something really fascinating to you that maybe you don't know a whole lot about, but that you've learned recently and was kind of a shock to you, or something that like just surprised you?
Yeah, I mean, before I got into this mineral resources research, I guess I just assumed that we had already figured out how much of a particular metal existed on Earth. And that's, I would say, there are estimates, there's good estimates, but drawing the line between what is a resource and what is, just the composition of the Earth is a whole different question, and one that's, been the subject of over 100 years of research, right? So to me, that is really fascinating. It's, what defines a resource is partly dependent on composition, chemistry, what's actually there, but it's also dependent on society and the value that humans place on a particular element or material. So, the economic side of things is really the thing that bounces around on short time scales, and people try to predict, and that becomes very, so there's multiple sources of uncertainty here. We understand pretty well how elements differentiate in the crust and the different processes that concentrate them. But beyond that, we also need to understand how they can be extracted, how they can be produced for a profit, and then what the value of that material is. And so that's been enlightening for me. I took a couple economics classes in college, and I'm not an economist, but I'm starting to consider myself an economic geologist, because you really need both of those to understand mineral resources in that way. So yeah, that's one of these open questions that it's like really surprising when I first got into it, that there wasn't a definitive answer. For example, like, how much copper is there on the planet that we could mine?
Mm-hmm.
And it's highly uncertain, is the answer. So
Yeah, as much as we'd like to have those numbers like be definitive and accurate, yeah, I think that's a really good example of just like how uncertain we are about things. Close, but not probably right on point. So that kind of brings me to my next question, because yeah, there's things about our own planet that we don't understand, but that we're researching, and we're constantly striving to sort of gain that understanding. And so my next question is kind of silly, but we like to ask this question to all of our guests, and that is sort of a hypothetical question. So let's just imagine that we're in a completely different galaxy, We're not in our Milky Way galaxy, we're in a different galaxy. And there's a planet that is similar to Earth, maybe the same size and sort of the same distance from its closest star. But maybe these rare Earth elements aren't as rare on that planet as they are here on the Earth. So how would you maybe solve a scientific problem on that sort of situation, on that sort of planet?
Yeah, that's a good question, and I like how you brought resources into it. So, you know, the the science side of things is all about, how are elements distributed in a planetary body, right? Like what processes are involved, what compositions. Um, I think that alone would be a fascinating research question, but I mean, now that you mention it, what's rare or scarce on Earth could be completely different on another planetary body. So let's say on this hypothetical planet, something that we think of as a high value commodity might be super common and therefore, of less value, right? And then something that we kind of take for granted as being abundant, uh, water or
Yeah.
maybe even a waste product or byproduct like CO2, that might be a rare, scarce material on this other planet. So it's probably too far to have realistic trade routes, but that's the type of thing that you would first want to answer those physical quantity questions. And then, I mean, if you could decide what like an optimum amount of rare earths for CO2 it could be, um, shuttled between planets. I think that would be kind of the well, I don't know. Now we're talking science fiction, but I think that's and the cool thing is you see that in science fiction, right? Even in Star Wars and these other fictional universes, that mining exists in people's imaginations too. So
Yeah.
I like that question a lot. Thank you for that.
Oh yeah, of course. Thanks for that great answer. We'll get NASA to start working on space travel better, and once we, learn how to fly at the speed of light, hopefully not break ourselves, then maybe some of these interplanetary trades can go on. But that's a great answer. I think like that's a great answer to sort of kind of a silly question, but yeah, something great to think about.
One more theoretical question, then maybe a little more realistic. If you were able to travel to a planet in our solar system, or a moon or whatnot, any body, maybe even a meteor, do you have one that you'd like to go to investigate or try to mine?
Yeah, I mean, I should be careful here. I'm not saying we should mine every
Yeah.
planetary body in our solar system. But I mean, just from a curiosity, I think Mars is the most Earth-like, and so therefore I'd probably feel the most comfortable in understanding what I'm looking at. Some of the other planets would be just so different from our own that everything I know about geology, if not completely out the window, would just need to be adapted or something. But yeah, I mean, Mars, just because it seems like some form of plate tectonics operated on it in the past, and the rock compositions are more similar as a terrestrial planet. Even some of the textures and surface processes, I think it would be really cool to like boots on the ground do field geology on Mars. But yeah, maybe one of my kids will. I don't know.
Totally. It could happen in our lifetime. Looks like it might, honestly.
Seems that way. Yeah.
Yeah, super cool. Um, well, that's great, Graham. Thanks for those answers. It gives us a lot to think about, I think, just as scientists, but as yeah, we have a lot going on this Earth, but there's a lot of other stuff going on other planets and in other places of our universe, and it's cool to sort of think about some of those hypothetical situations. I want to kind of return a little bit to your USGS work. I know you highlighted a little bit about how you got into the USGS, but can you just tell us what it's like working for the USGS and sort of what your role is within that agency? Like obviously you do the research, but are there other things that you're required to do or that you do just as ancillary work for them?
Yeah. So one of the kind of founding parts of the mission of the USGS is to classify public lands. So often in my work, we're asked to conduct mineral resource assessments, not explicitly for public lands only, but for a part of the country. And part of that is to help land management agencies, so the Bureau of Land Management, the U.S. Forest Service, make decisions about how to regulate different activities on their lands. So that's something, it goes way back to the Organic Act of 1879 when the USGS was founded by one of my personal heroes, John Wesley Powell. And just as an aside, a couple of years ago, I got to go on a raft trip down the Green River that started in Wyoming and through Utah and ending in Arizona, that commemorated the 150th anniversary of Powell's trip. So that was a highlight. I mean, that was, when you asked what are some of the most fun parts of my job, that I should have said that.
How long did that trip take you?
So I only got to do a portion. I was on the river for a week, but the whole trip was, a whole summer. I think it was 8 weeks. So some people started and ended and did the whole thing. But yeah, I was lucky just to do a portion in the Uinta Basin of Utah. I mean, it was spectacular.
That's
That's
awesome.
incredible.
Yeah.
But yeah, I mean, even today, 150 years later, we're still doing some of the work that was started back then and trying to understand the mineral resources of the United States and also plan, what is the best use for different parcels of land, right? That's kind of the government's role. But the nice thing about my job is, I'm a researcher. I'm developing expertise in a very narrow, it's kind of like when you do your PhD, right? You develop expertise in a very narrow field of subject. The USGS is set up similarly in that it has a very academic feel. Everyone works together in interdisciplinary teams. You might have an economic geologist paired up with a geophysicist and working together to try to answer particular questions. So that's one of the cool things about my job is, you never stop learning. I'm learning something new every day, and I find that really satisfying.
That's awesome. Yeah. What a cool way to what a cool career, I think, personally, but I might be biased because I've always wanted to work for the USGS. But do you have any advice for people like me or for students who are interested in working for either a state or federal agency like the USGS? Those are a little bit more competitive jobs. People get into them and they tend not to leave because they are awesome to work for. So do you have any sort of bit of advice on how to sort of get your foot in the door?
Yeah. I think often at least in my experience, there's a little bit of pressure to kind of specialize early, like even when you're an undergrad or early in grad school. And I guess I would encourage anyone who's interested in a career in public service, whether it's state or federal, you might need to kind of broaden your horizon, and that shouldn't be too hard. I mean, like I really struggled with the specialization because I was interested in all different types of geology and just really wanted to try to retain that general knowledge as much as possible. But it required, taking a little bit of a sidestep from the hardcore blinders on geochronology research I was doing to more general, like how do minerals interact with society, right? So that's one thing, is don't be too rigid on your kind of expectations of what what your career needs to be, because I think a lot of especially doctoral students can fall into that trap. But the other thing is, when you're a student, it's the best time to reach out, contact researchers that you're interested in their research. You know, there are pathways, they call them internships, for current students and recent graduates that are not open to the general public. They're only open to that portion of the population. So that's a real advantage for if you're a student, or within 2 years of graduating. Those positions are still posted on for federal positions on USA Jobs. So set up a USA Jobs profile, set up alerts for the type of position that you're looking for, the agency that you're interested in, and then getting contact information through USA Jobs isn't always the best way, but as a federal employee, my contact information is public. Many other researchers have public websites, so if you find someone and you're interested in their research, just contact them. Even if you can't be paid, you could potentially volunteer for a summer, and that might be a great foot in the door. So one thing about federal hiring is it's very process and bureaucratic in a way, and that's meant to protect people applying for jobs as well as hiring managers. But there's no substitute for the kind of interpersonal connections that you can forge at conferences and just meeting people. So the USGS does more than just rocks and minerals, right? There's 6 different mission areas. There's hazards, ecosystems, water resources, lots of different potential career trajectories. So I have nothing but great things to say about my agency. I love working there. I probably am in that pool of people who will stick around long term, but it is the other thing is not to be discouraged, right? Like I got many rejections applying to federal jobs before I got a position. So that's just part of the process.
Yeah.
It's good to hear. I've been applying. I'm about to graduate and been turned down quite a few times so far. So trying to not get discouraged, but
totally normal. And when that happens, you can always try to follow up and ask why, and they should be able to provide an explanation.
Cool. Good tip. Thank you.
Yeah, this is all great information. I actually volunteered for the USGS a couple summers ago at the Cascades Volcanic Observatory, and it was probably one of the best times I've had. One of the best volunteer experiences I've had with an agency. It was really fun to work with them and get to see firsthand what they do and how they do it. So yeah, I definitely recommend at the very least volunteering for them. It's something students and anyone else is interested in doing. Cool. So Graham, we do this little segment on our podcasts now and again, where we like to ask our guests how they would describe what they do to a different subset of groups. So we have 3 groups that we would ask you to describe what you actually do for research or for your job. And so the first one is, how would you describe what you do to an elementary school or to like a 4th or 5th grade class?
5th grader.
Yeah, that's probably the hardest one. Let's see. When I was in 4th grade, I think we had our rocks and minerals unit, and so I'd probably use that as a jumping off point and say, each one of these minerals occurs in a different type of rock in a different type of setting. And my job is to figure out which minerals and which rocks are distributed in which places. So I use maps, and I use especially geologic maps where people have gone out and looked at the rocks and colored them different colors on those maps. And that's just the starting point. Then I have to also consider, what makes a particular rock valuable. What metals or materials are in that rock that society needs to make things, products that we use in our lives. So
Awesome.
try to keep it plain language, but
yeah. I know
yeah.
it really is the hardest one. I was even an elementary teacher and I struggled with that question. I was like, I don't know. I study volcanoes. They're super awesome. Cool. So the next group of people is maybe a little bit older. So someone who maybe is in high school or even an undergraduate in school that you're trying to convince, maybe like what is so cool about your research.
Undergrad.
Yeah. So this one I actually have given lectures before. So I would say, so everyone has, a smartphone in their pocket or a laptop that they're taking notes on. And, often we think about these things as consumer items, with a particular lifespan. But we don't often think about all the materials that go into those products. So the phosphor screen on your iPhone needs europium to work, which is one of the rare earth elements, and the touch screen needs indium in order to make a conductive surface, and even the glass has different elements in it that make it rigid and so it doesn't break every time you drop your phone. So all of these devices have dozens of different metals in them. There's common ones like copper to make the electrical connections, and then there's uncommon or less common ones like tungsten in there that gives your phone its ability to vibrate. So when you think about all of the devices in your daily life, and then scale that up by the people sitting next to you, and then the other schools and universities around, and build that all the way up to the 7 or 8 billion people on the planet, that's a lot of material. And that material doesn't just appear, it has to come from somewhere, and ultimately it comes from the earth. Some of it can be recycled, and that's important, and it needs to be, to meet future demand. But there's also a growing population, a growing affluence of that population, so that new material needs to be brought into circulation as well. And so my job is trying to figure out where that material is going to come from. Where are mineral resources of the future going to be found? Which materials are more important? So, for example, do we need to build more cell phones, or do we need to build more automobiles, or do we need to build more, bridges and railroads and infrastructure? They all take different materials, different mixes of materials. Some are common, some are less common. It's all part of the research that I'm doing.
Awesome. That was a really great explanation. I also really liked how you related it to the cell phones. Something that I'm sure a lot of younger people are definitely curious about. And
yeah,
like
maybe even more than their foodstuffs.
Right, yeah. Like, hey, geologists don't just stare at rocks through a hand lens. Like, there's actually really important things that we do that actually relate to your device that you are so dependent upon. So Cool. And then the last group is basically professionals, like at a conference, which I'm sure you've had plenty of practice doing this, but how would you convey your research to professionals during a conference?
Expert.
Yeah. Well, I was at a conference last week, and
Perfect.
one of the topics, and this is just as an aside, I got into geology because I like rocks and being outside. Now what I do is more statistics and computer programming than anything else. So
Yeah.
it's almost unavoidable, and it's something, if I had advice to give myself as a student, whatever, 10 or 15 years ago, it would be take more computer science and stats classes, because that's what you need to be a scientist today.
Good point.
So for this audience, yeah.
I didn't learn coding until I started grad school. So, I mean, and it's used in everything. So, yeah.
Oh, I tried to avoid it as long as possible. I mean, and it wasn't until someone told me, in a crowded audience of people, they asked, who here thinks they're a modeler? And a bunch of people put up their hands, like geodynamicists, mantle modelers, and stuff like that. I didn't. And the next question was, who doesn't think they're a modeler? And I was like one of the few people raising my hands. And he's like, you're wrong, and this is why. Because whether or not you do computational models or statistical models, everyone forms a picture in their head of what they think, how they think the world works, right? Mm-hmm. And so even a mental model is a model, and models are useful. So if you can't explain even simple phenomena, just from what you consider intuition, but what really is a mental model, we wouldn't get anywhere in science. And that kind of made me appreciate kind of the advantages of modeling and what modeling can provide. So yeah, going back to your question, if I'm at a conference, and the main thing I need to explain is, what are the assumptions I'm making? What are the uncertainties associated with the results that I'm presenting? Because now, everything, a lot of the data I use is, legacy data or new data. It doesn't really matter its provenance, but it's being combined in a new way. And how that data is statistically analyzed and then incorporated into a model, including a geospatial model. So like how chemical elements are distributed in an area, for example. Mm-hmm. Those are the results that I'm presenting. So like going back again to what we were talking about, being honest with the uncertainties, being very clear about the assumptions, for that audience, that's what it's all about. That's I would say the scientific rigor of what I do and what others in my field do. Is it's not just can you predict where you might find like some gold. It's not like prospecting back in the 1800s. It's given these assumptions and these this understanding of geologic processes and this data, can you produce a result that other people can replicate using the same functions or parameters and that sort of thing. Mm-hmm. So not as interesting of a answer, but I think for that audience, that's really what, and you see it, people get into heated discussions about whether an assumption is valid or not, and that sort of thing. So there's always more to hammer out and improve on.
Yeah, I think you bring up some really great points. And also going back to, having different perspectives of what modeling means or what different processes mean to to solving a problem or to solving a research question. I think that's a really good point to bring up. We all come from different backgrounds. We don't all have the same expertise in these areas. Of maybe people are stronger in modeling and they like to be behind the computer, while others are stronger at, hey, I'm really good at identifying outcrops and I love to draw, and my visualization is on in a picture rather than like in numbers. So yeah, really great point. I like how you said that.
And it takes all of those skill sets. I mean, that's the other thing is, I think it's, I mean, not to compliment ourselves too much, but I think it's what makes earth science and geology so great is that so many different personality types are drawn to it, and they each bring different skill sets or a way of looking at the world, and you get to work with all these fascinating people. So I think there's a niche in the geoscience community for anyone who's interested in it.
Yeah, I agree. That's a great point.
So true.
Well, Graham, we don't want to, keep you too much longer. So I'm going to just finish up with a pretty serious question. So I would like to know, how many Lego bricks do you think it would take to build a bridge capable of carrying traffic from London to New York?
Wow. Okay. So it's got to be a fixed bridge. This isn't like a barge type situation.
Right.
Okay. Yeah, so I'm gonna go with like the standard, whatever, 2x6 brick. That's maybe we should probably use metric units. We'll say each brick is 5 centimeters, right? So that's 20 in a meter, and so that's 20,000 in a kilometer. And how many kilometers from New York to London? Let's see, it's about a 6-hour flight. Mm-hmm. So if you went the absolute shortest distance, going 500 miles an hour, I don't know that in kilometers per hour. We'll say
I'll look it up for you.
We'll say like 700 kilometers an hour, thereabouts. We don't need to be precise. Let's keep it 500 for round numbers at times 20,000. So now we're at 100,000, 10 million bricks, and that's for a single span. So now we also gotta how heavy is a car and how wide is a car. So let's say it's 3 meters wide times 3, and yeah, it's going to be a lot.
That's some really intense math for you on a Thursday morning. I'm really sorry, but that's excellent. This is like the processes that we go through. You like answered that perfectly, because scientists, this is what we have to think about. It's not just the number at the end. We have to think about all of the like features that go into, okay, like, well, how wide is a Lego brick, and how many bricks, would it take to just go from London to New York? And then also, like, how heavy is a car? I mean, it's pretty heavy. So it's not just, we put one layer of Lego bricks in there. We have to probably have several, like hundreds of layers of Lego bricks. So
yeah, no, that's a great question. And those are the type of questions that I get to use in my work all the time. So not Legos, but replace that with how many tons of rock do you need to move to make an iPhone, for example. That's
awesome though.
Same sort of problem, right?
Yeah,
totally. And putting you on the spot there allows us to really see your scientific process of how you deconvolve this question and try to answer it. So super fascinating. Thanks for that.
So do you ask everyone the same question, or do you switch it up?
Switch it up a little bit. We asked someone how many pennies could fit into a room once, different things like that. So general,
Cool.
same kind of trend to the questions, but yeah.
Yeah, usually the answer is a lot. That's what people get to.
Yeah.
Well, Graham, we really appreciate you coming on the podcast and sharing your thoughts. And you have so many interesting points and so many cool things to say about not only geology, but just working for an agency and also just the scientific process in general. So we really appreciate you coming on.
Well, thank you so much. And it was my pleasure. I also just wanted to acknowledge Professor Dan Luna for putting me in touch. And I look forward to seeing the podcasts you guys are putting out. I think they're great.
Well, Graham, thank you so much.
Thank you.
All right. Thank you guys. Take care.
Well, that was an epic conversation.
We'd like to thank all of our listeners.
Tune in next time for another Epic Earth podcast.
Crazy way to sort of sorry, I can't talk.